Okay, good afternoon, everyone. Let's get started. So first of all, just reminder, our homework 4 will be due, I guess, on next Tuesday. And then we'll have one last homework assignment. So don't worry, the workload won't be very high, but we still have the very last annoying final assignment. So the good thing is that we don't have any final exam. So just to be sure to finish your last homework assignment in time and submit your final project report in time, and that's it. Okay, any question about the homework assignments and the report, project report? Okay, so let us continue with Hamiltonian Monte Carlo sampling. So in the last lecture, we talked about how to leverage some dynamic system, physical system to generate sample proposals in the Markov chain Monte Carlo sampling framework, right? So we use a concrete example. It's called Hamiltonian system, right? So Hamiltonian system, you can basically view this like some spatial, like time spatial system. Where this spatial can be like 2-dimensional, 3-dimensional, or arbitrary dimensional, right? And it describes like if you have a big ball, right, without friction, and you have a small ball, like you initialize some state over this ball. For example, you give its position, right? You give some momentum, and then according to the physical law, right, this ball will move in this system, right? So basically, you can imagine this ball just oscillate, right, and moving around the surface of this big ball, right? And the idea is that okay, we can choose some time duration, like say t, and you just read out the state of this ball, including what is position, what is momentum, and use that as your sample proposal. Then throw some Mitropy-Hastings acceptance test to decide whether you're going to accept this proposal as the sample, as a new sample, right? This is how we integrate the Hamiltonian system into the Markov chain Monte Carlo sampling, right? So in general, you can use any dynamic system to generate proposals in the Markov chain Monte Carlo sampling framework, right? And it's not limited to Hamiltonian system; it can be any other system, right? And the general framework is like this, right? So suppose you got your current sample at step n, your Markov chain Monte Carlo simulation, right? Is the n, right? You really need to augment another independent random variable, Rn. This Rn usually is assigned some physical meanings, right? Like momentum, right? In Hamiltonian system, Zn corresponds to the position vector, which gives some potential energy. And the Rn, you random sample as the momentum, which decides what's the initial velocity, right? Including both the speed and also the direction, right? So, for the other dynamic system, typically you will give a similar kind of like augmented random variable as well, right? So once you generate this augmented variable, right, you pair this Z and Rn, you assign it as initial state for some dynamic system, right? And then you just evolve this dynamic system to a certain amount of time. So we denote this evolution by psi t, right? Psi means this physical system, t means that, okay, it will evolve along with a duration of time t, right? And then you put some operation over the state. So suppose you got Z, you got state V, you got state V, right? And then you put some operation over V, which we call R, to get your sample proposal. So regarding why you like why just the evolving dynamic system is insufficient, right? We need to put an additional operation over V to get your proposal. The reason is that I want to satisfy the reversibility, right? I want, starting from RV, this new state in the system, you use that as an initial state and then evolve the system to the same amount of time, T, and then doing the same operation, we're going to recover the original state. Why? Because we want to show the detailed balance, right? The detailed balance means that, okay, you start from initial state, you through some transition kernel, you get a new state. It is the same. I mean, the joint probability is the same as you start from the target state, right? And then you apply the same transition kernel, you go back to the original state, right? If you don't add this operation R, usually you won't be able to go back to return the original state. Then you cannot show the detailed balance. Then it's very hard to justify your chain, your Markov chain is valid. Does it make sense? Okay. So we got a general theorem, like showing that, okay, for any given dynamic system, how do we operate to generate a valid proposal and do the acceptance test to ensure that your Markov chain Monte Carlo sampling will converge to a target distribution, right? So this theorem we discussed in the last lecture. So let us just quickly go over it, right? So, and V equals to Z and R to denote, we denote this as our current state, or current sample in our Markov chain Monte Carlo algorithm, right? And then we evolve starting from V to a certain amount of time of T, we get V prime, right? Sorry, then we should change this to be V prime, right? Right? That means after certain amount of time, you got a new state called V prime. You can imagine for the Hamiltonian system, it might be this ball starting from here, and after a certain amount of time, you got this ball. And the ball here, you will have a different velocity and different position, right? That corresponds to V prime. And then we want the following conditions are satisfied. First, we got our operation R such that psi t is reversible on R, meaning that, okay, after I get my state through evolution of the of certain amount of time t, then I apply R over my state, get my proposal RV prime. Okay. And then if I use this guy as my initial state, I evolve my system again, and then with the same amount of time, and then apply R again, I can recover my original state V. That's called reversibility. So basically means, okay, psi t, if you apply R operation, it's gonna recover, it's gonna revert, it will be revert this process exactly back to the original state. Right? And this is a key to show the detailed balance. Right? And then the second condition is that this R operation must be in evolution, means that you apply R to X and apply R again, you recover X. In a Hamiltonian system, our operation is just to negate the momentum, right? So you negate momentum, then negate momentum again, it will just be the same as the original momentum, right? And if we use Hamiltonian system as the example, right? Uses your ball, right? You got a direction here, you got the position here, right? And your velocity here, right? And after a certain amount of time t, this is where your position, right? This is where your position, this is where your this is the direction of the velocity, right? So your R operation will be simply negate the direction of the momentum. That means you're gonna reverse the direction of the velocity, right? But you keep the value of the velocity, like keep the absolute value, and you keep the position. Then if you imagine that, okay, after I doing this negation, and then I initialize my ball in this state, right? I mean, starting at this position and with this momentum, I just run my Hamiltonian system with the same amount of time of t. We know that after time of t, my ball will be arrive at the same position, right? But the momentum will keep back, right, for this direction. And then I'm going to apply this operation again, right? Again, negation again. After applying this negation momentum again, we can see that your ball now is at the same position at the beginning, and your ball has the same momentum as the beginning. So that means you exactly recover the original state. Does it make sense? Right. So in this way, you can show that okay, your transition kernel essentially, right, is to apply R over psi t evolution of your initial state, right? And you can show that okay, through this transition kernel, the detail balance is satisfied. But if you want to see rigorous proof, we have listed the someone's PhD thesis in our course website. You need to do a little bit of work to prove that, because this transition essentially is a deterministic transition, right? You first evolve your physical system and then do some operation that both steps are deterministic. And if you translate it into a probabilistic language, it's called delta prior, right? And you need to show that your condition distribution is the delta distribution multiplying with some distribution. It is the same as you do it reversely and multiplying with the distribution, right? You need to show that. Okay. And then the third condition is that, okay, after I get my proposed sample, right, RV prime, right, I'm going to use this rule to accept it. How can we accept it, right? We're going to calculate the probability. This probability is the you evaluate the target distribution at RV prime, namely our proposal, and divided by the target distribution evaluated at the original state V, right? Multiplying with this Jacobian, right? This Jacobian just means the Jacobian of the proposal with respect to the original state, right? And you can calculate a probability. If you use this probability to accept your proposal, and then your whole procedure is valid, meaning that you keep running this Markov chain to guarantee to converge to this target distribution P of V. Does it make sense? Yeah. Are we on the same page in understanding this theorem? I'm just talking about the theorem. I'm not talking about how to prove that. And again, you are not required to prove this, but if you're interested, you can take a look at our reference. Right? It's not hard, but it does need some. You need to take care of something. Okay, so and then we can just apply a Hamiltonian system to this proof, right? And say why is this correct and why is this effective, right? So first, you have Hamiltonian system. We know the psi is just evolution of Hamiltonian system, and R is a negation of the momentum. The interesting thing is that when we do this Metropolis-Hastings test, acceptance test, right? You see that because Hamiltonian system will preserve the energy, right? Remember, the target distribution, right, of any state V is proportional to the exponential of negative entropy, right? Negative total energy. Right? But when we evolve a Hamiltonian system, this energy doesn't change. That means this fraction is simply 1. A second nice property is that the evolution Hamiltonian system guarantees that this Jacobian is always 1. Then it tells us the right term of this mean function is 1, right? Mean 1 is just 1. So if you use Hamiltonian system to generate a proposal, your acceptance rate is always 1. That's a very nice thing. Or in other words, that's why Hamiltonian system is the most popular choice of dynamic system to generate sample proposals, because it's always fun. Right? And in theory, you can evolve your system to arbitrary long time, right? Right? Because it doesn't change the energy, and the energy is also conserved. So this guy is always one. And evolve it for a long time, it means that you are able to change your initial sample Z, right? Very large, right? So that means you can very efficiently explore the whole sample space, right? Without damaging your acceptance rate, right? That's a very good thing. I remember when we talk about the other Markov chain Monte Carlo sampling, right? We talk about that, okay, for a Gibbs sampling, what we can guarantee acceptance probability is always one, but due to the strong correlations between the random variables, right? Every time you can move only a tiny bit, right? You cannot move very far away. But here, the Markov, the Hamiltonian system not only guarantees acceptance probability 1, but also allow you to move arbitrarily long distance. So it means that, okay, if you use that to generate samples, you can explore the whole sample space very, very efficiently. Right? That's why it's so promising. Any questions so far? Okay, but now let us go back to reality. We are not able to exactly use this system to generate sample proposals. Why? Any thought? In other words, we can't guarantee acceptance probability to be 1. Any guess? Yes. Because those are just the ideal, I mean, theoretical properties, right? If you can exactly simulate Hamiltonian system well, you can achieve all those good things, right? But the problem is that you are not able to exactly solve this system or simulate this system, right? If you look at the Hamiltonian system, the rules of this system, right? We know that there are actually a set of ODEs, ordinary differential equations, right? So you can see that those are just the function of time, like ZIT and RIT, right? So for convenience, we didn't explicitly write out time t, right? So those are called ordinary differential equations. And what you need to do is that you're going to set Z0 and R0, right? As we mentioned, Z0 and R0 is your current sample in your Markov chain. And R0 is just random sample from your prior distribution, right? And then you solve this system, right? When you exactly solve this system, that means you can exactly simulate Hamiltonian system, then all nice properties are there. But unfortunately, we're not able to exactly solve it. And in practice, first, it doesn't have any analytical solution for this, in most cases. And that means you have to use numerical integration. Okay? For any arbitrary, for any ordinary differential system, right? So let me write down something like x0 equals to u and dx or dt equals to fxt, right? This is a general form of the ordinary differential equation, right? If you solve it, we know that the solution will be xt equals to x0 plus some integral, right? And fxt, fx tau, d tau, right? The problem is that you are not able to exactly compute this integration. Right? Because you see this f, right? This f represents derivative. This derivative is also a function of x itself. You don't know exactly what x is at any time. You will not be able to compute its derivative, right? So actually, when we do this integration, it is we won't be able to give the exact form of this. Then, how can we address this problem? The question? Okay. the practical choice is called numerical integration or approximate integration. If you do the approximate integration, that means your computation of those states has some errors, right? It has some errors, of course, it won't give you acceptance probability one. Does it make sense? Any question regarding this point? David. So your acceptance rate is related to the error of numerical integration, but it's not like directly related. You see that because I will talk about that later, in a minute. But you see that because of this error of numerical integration, it cannot conserve the energy. If it is not conserve the energy, then the ratio of these two probabilities are not just one, right? It will be less than one. It will be less than one, that means your acceptance probability will be lesser. Any other question? Okay, great. So let's see in practice, right? How can we simulate Hamiltonian system? We can use numerical integration, and one most commonly used, perhaps the simplest approach is called Euler's method. I bet everyone of you have heard of this before. Right? So what does Euler's method mean? Right? So if you want to integrate a complex function, right, through 0 to some ending time t, right? So the method is that, okay, I'm gonna choose a very small step size, right, to partition this time range into many, many small steps, right? So the step size is denoted by epsilon, right? The Euler's method assumes that, okay, because this step size is so small, so the gradient of my function, like dz over dt, right, during this very small tiny time interval, can be approximated to be constant. I can use the gradient at any position inside this interval to approximate. One of the most commonly approximations that, okay, I'm going to use the gradient at my starting point. Here's t plus epsilon. At my starting point, as my gradient. Then, if I want to get zt plus epsilon, that means the state after this epsilon step size, I simply multiply this gradient with this step size epsilon, right? That's the idea. That's Euler's method, right? Any question? Okay. Of course, you can approximate the gradient in this interval as some constant, which is the gradient at the ending point in this small time interval. That is also feasible. It's called backward Euler, but backward Euler usually is more difficult to compute than forward Euler. So then, if we use this idea, we can definitely simulate our system. Like, for example, if I want to compute the ith momentum element at t plus epsilon, right? We can start from a state at t, right? Then multiply, because I'm using the gradient at starting point, which is t, as my gradient approximation. I time epsilon, right? And this DRIT, we know that according to Hamiltonian system, which is just the partial derivative of the corresponding partial derivative of the potential energy at Zi, right? And similarly, you can evolve your position vector, right? Using the same rule, right? But Euler's method has some issue. It is very simple to implement, but its accuracy is not very good. So Euler method is called the first order method. meaning that your error is proportional to some constant multiplying with the step size epsilon. So basically, if you reduce your step size by factor 2, that means your error, your approximation error, your whole approximation of this integration will be reduced by the same factor 2. Right? That's not very good. So in practice, people often choose a second order method. It's called leapfrog, right? And it has a much better error rate, which is squared to the square of the step size. So what does it mean? It means that if you reduce your step size by half, then your global approximation error of your integration will be reduced by a factor of 4. So sounds very good, right? So what is the leapfrog method? It's a very smart design. Right? So we know that we're gonna evolve both the momentum R and position Z, right? So Ri and Z are just the ith element, your momentum vector and the position vector, right? So it introduces a concept called half step. Right? What does it mean, right? You can define your step size to be epsilon, right? Draw it a better way. This is your step size, epsilon. Your goal, like every iteration, the goal is that, okay, I want to compute my state at t plus epsilon. But I'm not going to directly apply Euler's method. Instead, I'm going to first compute the state at half of this interval, namely Ri t plus half epsilon. And how can I get the state of Ri at t plus half epsilon? I'm still going to use Euler method, meaning that I'm going to compute the gradient of Ri at the starting time t here to approximate to the gradient in the first half interval, right? So we know that this guy, dri over dt, is actually partial, negative partial of uz over partial zi. U is the potential energy, right? The corresponding zi. So that means you need to compute your u gradient as zi here, and then you treat this as a constant gradient. You just multiply half epsilon, right? You get your intermediate state of Ri. Right? And next, we're going to compute ZIT plus epsilon, meaning that I want to compute this guy. As we mentioned, right, we're going to still approximate the gradient in this small range as some constant, right? But I'm not going to use any gradient, right? Here or here, here or here. This, we're going to use this gradient at these two ends. Instead, I'm going to use the gradient in the middle. Okay. So this gradient in the middle, we know that ddi over dt plus half epsilon, this is in the middle, right? It is computed based on Rit plus half epsilon. So thereby, we're going to leverage the intermediate state we just computed for I to help us to get to the target state of Zi. So got Zi plus T, Zit plus epsilon. Right? And the third step is that, okay, I'm going to start in of my half step state Ri to arrive at my target state Rit plus epsilon. How can I do that? Now I'm going to use my ending state here to compute, to calculate the gradient of Ri. So we know that dRi t plus epsilon over dt equals to the gradient of potential energy over Zi at t plus epsilon, right? So you're going to leverage this state to compute your gradient of Ri at any state time and approximate as a constant through the second half range, right? And then you just apply it again to get your Ri t plus x. So you can see that this path is like frog jumps, right? That's why it's called leapfrog. And through this smart design, I mean, numerics that I'm showing that this kind of cheap second order error. And someone may ask, right, is there like even higher order numerical integration approach, right? Say I can get epsilon square, epsilon cubic equals epsilon fourth order of error. The answer is yes. This is called the high order symplectic integrators. But we'll use even higher order method to do the numerical integration. You will see that the computation cost grows much faster. That's why, like, to best trade off the computation cost and the error, most people will just use second order method, namely the leapfrog. Any questions so far? Okay, then we can use a leapfrog method to simulate our system, like using the same framework we just discussed, right? So we're starting from state ZT, which corresponds to our Markov chain, right? It corresponds to the sample hour in step n, right? Then you randomly generate some momentum vector Rn, you pair it as initial state of your Hamiltonian system. And now I want to look at what's the state after amount of time s, right? I can just apply leapfrog method we just discussed, right? Through this numerical integration, right? We'll arrive at your new state, z t plus s, r t plus s. We're going to apply the negation operation again. So this is our sample proposal. But this sample proposal was generated by running the leapfrog numerical integration, right? It's not the ideal Hamiltonian system, right? And the good thing is that even you use leapfrog method for numerical integration, right? It's different from the exact simulation of Hamiltonian system. It still satisfies this reversibility. So that means, okay, if you simulate your system with your leapfrog, right, and then you do the negation, this forms your transition kernel. And guarantee that starting from your proposal, you run your leapfrog again and do the negation, it will exactly recover the original state. So it's still satisfied due to bias. And this can be much easier to verify, but just looking at this. You can try to write down the update procedure, right? And then you starting from your negative r t plus s, and then you do then you just integrate again until you reach ZT and RT. You see that it exactly matches. But this check, I did that before. It's a little bit tedious, but it will be interesting if you can do that. It will definitely deepen your understanding of this algorithm details, right? And second property is that still preserve the volume. That means even you use leapfrog to simulate, right? Every time step, you got a new state, right? See, Ri t plus epsilon and zi t plus epsilon, right? The Jacobian of this new state with respect to the original state, the determinant is still 1. That means no matter how many steps you run your leapfrog, right? Your new state, the Jacobian of new state with respect to the initial state, the determinant of that Jacobian is still 1. So that's a very nice property as well. Does it make sense? Right. So this is also very easy to check. Why is very easy to check, right? We can check it by ourselves, right? So we want to know, like at each step in the leapfrog, how can we get RIT plus epsilon, ZIT plus epsilon from ZI, T, and RIT, right? And it turns out that you can write it down as a matrix A. And the determinant, so the Jacobian essentially is A, right? Because it's just a linear function. The derivative of this guy over derivative of this guy will be A, right? You will see that this A can be written as B and times C, and B and both B and C are triangular matrix. So that means the determinant must be 1. Okay. How can we see that, right? So first, we can take a look at, because this is the last step, right? So we know that it is directly come from Ri T plus half epsilon and Zi T plus epsilon, right? Right? This is the last step of your leapfrog. So if you look at their transformation, right? So this guy is simply, this is 1, this is 1, this is 0, right? Because if you want to get ZIT plus epsilon here, this is already ZIT plus epsilon. And this one is just minus half epsilon times something, right? So you can see that this is triangular matrix, right? So this determinant is 1. And if you look at this, right? This intermediate state, how it is come to this intermediate state from RIT and ZIT. Sorry, from RIT half epsilon to ZIT, right? That's the second step, right? So this step is also a triangular matrix, because why? Because this guy doesn't change, right? That means this is 1, 0, right? And this guy is changed because this is the older step, right? So you're gonna have something here and times 1. So you can see this is still a triangular matrix, right? And diagonal elements are 1. Right? And then if you use this guy to look at how this is generated from the original state RIT and ZIT, you see that this is also only 1 element change. The other element won't change, so it will give you 0, 1 in 1 row, and the other one is a 1 something else. Right? So you can see the 3 steps is actually fix 1 element and just update another element as just linear update. So this is called shear transformation, and shear transformation won't change the determinant of Jacobian. Again, if you do not completely follow this, this little one, I just want to give you a sense like why I'm doing this leapfrog is fancy, it's great, right? Because it can keep this so-called volume preservation property, essentially keep the determinant of Jacobians 1. And again, if you're interested, you can sit down at your table and try to do this. Right? It's not hard, and you'll see why it's nice. Right? Okay. So you can see that if you use numerical integration to simulate Hamiltonian system, we have nice property of reversibility. We have nice property of volume conservation. But the last thing is the conservation. So note that for the exact Hamiltonian system, the energy doesn't change. You don't leak any energy. You don't consume any energy. So energy conservation is solved, right? But what if you use numerical integration? We still keep the total energy invariant. And if not, it's not, right? Why? Yeah, because numerical approximation error, right? It's like you run this ball, but there's some friction here. There's some friction, so that when you simulate compute, the friction will just consume part of energy. Right? And the smaller step size you choose, the amount of energy you lose will be smaller, but there is always some energy loss. Right? So they won't conserve energy anymore. In general, you run numerical, you run a numerical integration to generate a proposal. This procedure can be viewed as dynamic system as well, right? As you mentioned, this theorem does not only apply to physical system, right? It applies to any dynamic system. You can use any rule to evolve, right? So now if we apply this proof or this theorem to our leapfrog-based system, let's see what will happen. So first, psi t now becomes the leapfrog simulation or numerical integration procedure, right? And then your R here is still negation of the momentum. You said that R is involution, and also running leapfrog, you're doing this R, it still guarantees the reversibility, right? And then we can take a look at acceptance test, right? For the acceptance test, to ensure that your proposal generation based upon leapfrog is valid, you have to conduct this test as well, right? That means you have to compute what is the ratio of your target distribution evaluated at your proposal and evaluated at your original state, multiplying with this absolute value of the determinant of the Jacobian, right? So first, because the volume preservation property of leapfrog, so this guy is still one, right? It's actually the most headache, the biggest headache. I feel it doesn't work. It does not necessarily work for every dynamic system, right? If you can use arbitrary dynamic system, well, that means you need to be able to compute the Jacobian for arbitrary dynamic system evolving for a long time with respect to the initial state. That won't be a good thing, right? That won't be a funny thing. So this one on the leapfrog system is still one, right? And this one will not be, this ratio will not be one anymore, right? Why? Because the energy does not preserve anymore, right? Energy does not preserve anymore. So because when we evaluate, it will also lose some kind of accuracy. So this guy will always be less than one. So yeah, that means your acceptance probability will be less than one. That's in practice how you apply Hamiltonian one-house sampling, because you're actually not able to exactly evolve the phase system. You have to switch to some numerical integration scheme. So typically leapfrog. So that means your acceptance probability will be less than. Does it make sense? Okay. But it's not too bad because if you choose your steps epsilon to be enough small, you can view like numerical integration error is still relatively small, right? That means this ratio can be very high, like 0.95. So it's a pretty good ratio to accept new proposals, right? So that's not bad. And actually, we'll discuss about it later. In practice, people will run HMC, right, to accelerate the exploration of whole space. And they will try to run this leapfrog for a long time. We know that the longer time we simulate, the less accurate, right? Because your numerical error accumulates along with the time steps. Right? That means this acceptance rate will keep decreasing. Will increase the number of steps, and they will usually choose tune that to make your acceptance rate to be 0.6 to 0.7 to ensure that okay, you can start from here, and then your next sample can be here, can be very far away, so that it can accelerate the exploration efficiency for the whole space. for the whole sample space. Okay, so now we have discussed the critical step, how we use Hamiltonian multi-level sampling coupled with some numerical leapfrog algorithm to generate a new proposal, right? And then we need to supplement the remaining things about how to generate momentum variables, right? So basically, suppose this is our drawing distribution, which is over the random variable z and the observed data d, right? So we assign z as our position vector in the Hamiltonian system. So we assign the position, we assign the potential energy at this position as negative logarithm of the drawing probability, right? And then we introduce a momentum random variable. This is how we define the potential, the kinetic energy, right? So the kinetic energy essentially it corresponds to some Gaussian distribution with the covariance matrix M, right? And M is really taken to be diagonal in practice. So, and this kinetic energy essentially is also the negative logarithm of the prior of the distribution of R, right? And then that means our joint distribution of Z and R in this augmented system is proportional to exponential to negative total energy, right? And we know that because R is totally independent to Z, right? So this is essentially P of Z D times P of R, right? So it doesn't change the system at all. Why? Because when you integrate R, you recover the original model. Okay. And then our goal is that we want to construct a Markov chain multi-level sampling algorithm to generate samples from this P of Z and R. Well, it more rigorous speaking, it should be generated posterior of Z and R given D. Right? This is posterior distribution, but please be careful because R is independent of Z. So this guy essentially is P of Z given D times P of R. Right? Because R is independent of Z, the condition. It is condition D. Even it's condition D, it doesn't matter, right? The data D doesn't have any effect on R. So the posterior distribution of Z and R given D is just the posterior distribution of Z given D times the prior distribution of R. In other words, we can also say P of R given Z and D is also P of R, right? Because R is independent of Z is independent of D, so the condition distribution is the same of the marginal distribution. This is a basic property of the independence. So now let us look at the whole frame. Right? To generate a new sample in my Markov chain based on Hamiltonian system, right? First step, I'm gonna sample a momentum random variable through the Gaussian prior. So here I just write it as itemwise, but you can view it as R vector sampled from the normal distribution with diagonal covariance matrix S, right? It's the same thing, right? And next, I'm gonna pair my sample R with current sample of Z, right? Together to initialize my system, Hamiltonian system. Then I run my leapfrog for L steps with step size epsilon to get Z prime, R prime, right? And then I negate my momentum, get R minus R prime. This forms my new state, your sample proposal, which is Z prime R minus R prime. Okay. Then I'm gonna run this acceptance test, right? With That means we're gonna accept my new sample, my sample proposal with this probability, right? So this one is actually just apply here, right? So remember for the Hamiltonian system, even for the leapfrog, this guy is 1, right? It's just the ratio of the target distribution evaluated at the proposal, and the target posterior distribution evaluated at the initial or original state, right? So that's how we get here, right? And then if Z prime is if this sample proposal is accepted, you just keep it. But because we only care about Z, right? So just keep Z prime, right? Otherwise, you keep Z. So this is a typical Mitropi-Hastings acceptance test, okay? And then finish these 2 steps, you got a new sample at the next step, Zn plus 1. And then you do this again, you get the next example of Z and continue until your Bernoulli stage has arrived. Does it make sense? Any questions so far? David? Yeah, that's a very good question. So, well, your T usually decomposed as 2 parameters. One is number of time steps L, and the step size epsilon. So in practice, the choice of this L and epsilon is very critical. You need to very carefully choose these 2 hyperparameters to run your Markov chain, and it's very sensitive actually. But the choice of them is like cross validation. You can definitely use cross validation or held out data set to choose them. Another thing I want to mention that the step 1 is like keep sampling step. Although we sample R from the prior, right? So this one is like I'm gonna sample R given Z and given time given the data D. Why? Because R is independent of Z and D. So this conditional distribution is exactly the same as the prior of R. That's why you directly sample R from this prior. It is equivalent to sample R from this conditional distribution. So you can view the step 1 as a keeps sampling step, and then step 2 is a Mitropi-Hastings step. So from our previous analysis, we see that keep sampling step essentially is also a valid Mitropi-Hastings step, right? The acceptance probability is 1. So if you couple multiple Mitropi-Hastings step together to form one joint Mitropi-Hastings step, it's still a valid chain because it guarantees that your target distribution is invariant to the transition current. So it still guarantees that your chain will converge to the target distribution or target posterior. The second thing is that, as we briefly discussed before, you need to be careful about ergodicity, meaning that you run your Markov chain this way, you are still able to have non-zero probability to jump from any sample in the sample space to any sample in the whole space. This is called ergodicity. And in many cases, as long as this guy, Ri, the prior is flexible enough, meaning that your distribution has non-zero value, density value at any sample in the sample space, that should be fine. But if it happens to have that, okay, after you run a leapfrog, it has some periodical behavior. That means, okay, starting from this state, it will run, and then it returns to some previous state. Then it might cause some reducibility in your chain. And in general, if you happen to that, right, you need to randomly adjust the step size and also the number of steps to overcome this. But again, this situation happens like really when you design a brand new Hamiltonian Monte Carlo algorithm. But in most cases, for example, if you just use Gaussian and you don't have weird joint distribution, that won't happen. Any questions so far? Okay. So now we have finished the discussion of Hamiltonian Monte Carlo sampling. So what kind of applications we prefer to use Hamiltonian Monte Carlo sampling, right? It can only apply to continuous distribution, meaning where the random variables must be continuous, right? If it is discrete, it is not applicable because you have to compute the gradient of the log joint probability with respect to random variable, right? Remember in our Hamiltonian system, your derivative of your momentum is negative derivative of log joint probability of the data and random variable z over dz, right? This is called the potential energy, right? That means z is differentiable, meaning that z must be continuous. So it's so in general, it's a very powerful Markov-Chain Monte Carlo sampling, and usually much better than the the ordinary Mitropoli-Hastings algorithm. And for the Bayesian neural networks, especially fit-for neural networks, it is a golden standard if you want to do probabilistic inference. And as to the choice of epsilon L, right, there's a trade-off. Right? If you use large step size and a large number of time steps, right, it will allow you to explore the space further away, right? That means if you choose a larger time step or step size or very large number of time steps, you can evolve your z from here to very far here from zero, right? But then it accumulates more numerical error. That means it lowers the acceptance rate. So there's a trade-off. So if you choose small epsilon, small number L, right, it can be quite more accurate, say make your acceptance rate to be 0.99. However, you might just evolve z from some position very nearby. This might not be something you want because we want to quickly explore the whole sample space, right? So in practice, you have to make the choice, make the trade-off by yourself. Okay? There are some more advanced algorithms which can automatically tune epsilon L. It's called no U-turn sample. No U-turn sample. It has a brief name called NUX. Okay. If you're interested, you can take a look at this algorithm. Very smart. And if you run it, you don't need to worry about how do you set up epsilon L. It will automatically adjust it for you. And that should be integrated in many standard package. Okay. So now we have finished our introduction of Markov-Chain Monte Carlo sampling. Again, this is a giant topic, and this topic has been developed for at least 50 years. Right? So we won't be able to cover all of them like in 3 or 4 lectures. But we do believe we have introduced all the fundamental ideas and the basic strategies, right? And in the future, if you want to dive into this topic, you will have like right sense and have the basic knowledge. Right? It won't feel very difficult. So we expect you to understand the basic idea of Markov-Chain Monte Carlo sampling. And the case concepts to construct such a chain, like how to design transition kernel, what is the so-called stationary invariant equilibrium distribution. They are basically meaning the same thing. Like what is the distribution your chain finally converges to, right? And what is DTO balance, right? Is actually sufficient condition to guarantee that your chain will converge to some target distribution, right? And you should know what is the general framework for Mitropoli-Hastings. And if you use just symmetric distribution, the general proposal, if you cause random walk behavior, what is random walk behavior? Why is random walk behavior is a nightmare? We don't like it, I think. And they should know the idea of gap sampling, right? And what's the problem, right? The gap sampling can well address the random walk behavior, but because its acceptance rate is 1, but because the strong correlations between random variables, it can limit the efficiency of exploring the sample space, right? And then hybrid Monte-Carlo sampling can further address the problem of gap sampling because you use homogeneous system to evolve to generate proposals. It allows you to expose the space much more efficiently. Right? But of course, you need to trade off to the acceptance rate. And we finally expect you'll be able to implement those algorithms. Although in our homework assignments where we do not require you to do so, probably you will be asked to implement some simple version of this algorithm. Right? But in practice, it will be much better if you can implement those algorithms. Okay, any questions so far about Markov chain Monte-Carlo sampling? Okay, great. So the remaining time, we're gonna start with our new topic. It's called Bayesian neural network. You know that neural network nowadays is the mainstream of machine learning topic. Right? Maybe 70 or 80% of machine learning venues are all about neural networks, right? Propose all kinds of weird structures, right? Claiming they're good. Right? So from a probabilistic person, right? From a probabilistic perspective, we would like to know, okay, if I want to learn something in a probabilistic word, how do we quantify the uncertainty? Right? How do we know the distribution, the posterior distribution of the neural network's parameters and neural network's prediction? Right? This is called Bayesian neural network. So we're going to first briefly introduce the framework of neural networks and the idea of backpropagation. If you have taken my introduction to machine learning course before, you might now be unfamiliar with backpropagation. But here we're going to use matrix vector description of backpropagation to give you a more general sense. Right? We'll not get into the details. And then we'll introduce the most popular optimization framework in the machine learning world is called stochastic optimization. So right now, nearly all the modern neural networks are trained with stochastic optimization rather than deterministic optimization. Right? There are some reasons. Right? Then we're going to introduce the framework of the Bayesian neural networks, and we'll talk about some classical Bayesian inference for neural networks, which is called Bayes by backpropagation. And we'll introduce the so-called reparameterization trick. So this is actually a very, very popular trick for Bayesian inference. You'll see that it is simple, yet very, very powerful. And then we'll introduce two typical or commonly used Bayesian networks. One is called auto-encoding variational Bayes. This is very often used for, image-related applications where you want to compress the image. And the other is called general adversary networks. This was a very hot topic maybe a few years ago. Right now, general adversarial neural networks are replaced by the so-called diffusion generation modeling, which is another more complex probabilistic model. Due to time limit, we're not able to introduce that type of framework. But I do believe that if we know all those well, it's not hard to learn that so-called general diffusion framework. Okay. So first, neural networks and backpropagation, right? So neural networks are kind of a very old topic. It can be traced back to like 1943, right? Starting from some research of the psychologist, right? And then people are developing more and more powerful and more large neural networks. And so I think at the beginning of this century, like 2005 or 2006, there's some resurgence of neural networks. And with the growth of computation power, especially the GPU usage, the application of the training of extremely large neural networks becomes possible. Then people start to realize the power of neural networks. And neural networks are inspired by some biological neural system, but again, don't be confused. They actually have nothing to do with biological neural networks. And in fact, I discussed with some guy in Google Brain previously. I asked them, did you guys try to like simulate a real, kind of like real biological neural networks? They said they tried, but the performance is much worse than just using the artificial neural networks. And as to why, they don't know. They don't know why. But the thing is, if you want to make your neural network work, you are not able to. You shouldn't pick up those elements in the biological neurons. Right. So modern artificial neurons are inspired by biological neurons, but there are many fundamental differences. Don't take the similarity seriously, and don't take the claims as in the news about the emergence of intelligence behaviors, including ChatGPT. Right? So yeah. So okay, what is artificial neural network? From the mathematical perspective, you can view it as a type of function. This function has a certain structure, which converts the inputs to the outputs defined by a directed acyclic graph. Here we just talk about feed-forward network or multi-layer perception. But if you know more about neural networks, you know right now there are many variants of the architecture, so you can plug in all kinds of structures. Right? Let us stick to the classical structure. Right? So you can see the input is at the bottom level of the neural network, and every time your input is first do some transformations through the weights on those edges, and then through some nonlinear activation function to get the output of this layer, and this output layer is sent to the next layer. Then you do linear transformation, nonlinear activation again, and send to the next layer. You do this sequentially until you reach the output layer. Okay. So to define a neural network, we need to specify first the structure of the graph, namely how many layers do you have, how many nodes do you have for each layer, and how do these nodes across different layers connect. And then you need to specify the activation function on each node. Okay? And third, you need to specify the weights on those edges. And usually, the weights of those edges needs to be learned from data. And the structure and the connecting patterns of the neural network will be specified during your design of neural network. Okay? This design is also called architecture. So the choice of activation function is many. Right? So you can use linear unit that basically doesn't do anything. You can use thresholding unit. You can use sigmoid. You can use rectifier, linear, root, and tanh. Right? And right now there are many other variants like a CLU. Right? It's a sigmoid times some function like it is to simulate the ReLU, but it wants to make your activation function differentiable and continuous. Right? So here we have an example. Maybe I have seen this before, right? So given the input X, how do we compute your prediction, namely the output of your network through the so-called forward pass, right? So this is the input layer, right? X0, X1, X2. And then you're gonna sequentially compute every neuron in the next layer, right? For example, if you want to compute Z1, right? You're gonna first do a linear combination of the incoming neurons, right? Through the edges on the through the weights on the connected edges, right? And then you apply some nonlinear activation function sigmoid. You get the value of neuron Z1, right? Similarly, you're gonna compute the value of neuron Z2, right? By a weighted combination of X0, X1, X2 again, but weights are on different set of edges. Usually they're different as well. Like then you apply the nonlinear activation function as well. Right? And then once you have collected the neurons in the second layer, those neurons will be combined together to calculate the input to the next layer. But here we only have three layers. That means in the third layer, there's just the output, right? In the output layer, you simply just do a linear combination of the incoming neurons rather than doing some nonlinear activation function. This is just traditional neural network iteration. Any questions so far? I assume this is, I mean, everyone is not feels does not feel strange about this. So I go this very quick. Okay, I go through this very quick. Okay, and then how do we train our neural network? Namely, how do we estimate the weights on those edges, right? So the standard way is to construct some loss function. You got your observation of your output y star, right? And your y is computed based upon the input and weights, right? So actually it is a function of the neural network weights and their input vector, right? So then you just calculate the loss of your prediction. And suppose you have many data points, you just summation over the loss of the prediction at every example. You got a function of, you got an objective function for your neural network weights, right? Then you just minimize loss to learn the weights of the neural network, right? Okay. So in a more succinct representation, right, we can use vector and matrix views to illustrate neural network. In general, we can represent an L-layer neural network, feed-forward neural network in this way. Okay? So we assume our input is a D0 dimensional vector. So this is a X0, which is the first layer, right? Or zeroth layer, whatever, right? And then we're gonna compute the output for every layer, right? So we denote output for every layer by X0, X1 until XL minus 1, and the output of the output layer is just XL. So without loss of generality, we assume, okay, the dimension of output in layer 1 is D1. Dimension of output in layer 2 is D2. Dimension of the output at L's layer is DL, right? Then the rule to sequentially compute the output of the neural networks layer by layer is as follows. So if you want to compute the output of J's layer, so Xj, we're gonna first do a linear transformation over the output of layer G minus 1, right? So this linear transformation can be written as a matrix multiplication. So there's the weight matrix Wj times Xg minus 1. And then we'll apply an element-wise activation function over this. We get the output of the J's layer, right? And the weight matrix Wj is the size of dj times dg minus 1. As we mentioned, when we do matrix vector operations, we also need to check the size of the matrices, right? So we know that the output of G minus 1's layer is dg G minus 1 times 1, right? Then we'll multiply this transformation matrix Wj, it will give you dj times 1 vector, right? Then you do analyze activation function, you got the xj, which is dj times 1. Right? And then you get xg, right? And again, you use xg as the input to the layer g plus 1, right? Then you first do a linear transformation, that is wj plus 1 times xj, and then you do an analyzed nonlinear activation function, you get xj plus 1, right? You just keep doing this until you arrive at the last layer. But the last layer, remember XL, we don't do activation function, we just do a linear combination of the incoming output, which is XL minus 1. Right? So this is how we compute the output of the last layer. Does it make sense? Right. So, yeah, this defines succinctly how we compute the output of each layer in a neural network, right? And to represent the output of a neural network parameterized by this W, right? The input is vector x0. You can also written it in a recursive way. Any questions so far? So if you want to compute the prediction of the output, right, we need to sequentially compute the output of every layer, right? Starting from x0. X0 is the input vector, or feature vector is naturally served as the output layer, output of the first layer, right? Then use that to compute output, output of the zeroth layer. And then you use that to compute the output of the first layer, and then second layer until the last layer. So this procedure is called a forward pass. Then that brings the question, right? In the training, we know that we're going to construct the loss, right? We have a set of examples, right? And then we just compute the square loss, the mean of the square loss of using our neural network to predict the output, the observed output in the data set, right? Then there's a question, how do we compute the gradient of our loss with respect to all the neural network parameters? We know that an efficient computation procedure is called backpropagation. So different from the forward pass, the backpropagation computes the gradient and propagate intermediate results in a reversed way, namely starting from output layer and move one layer preceding each time and until you reach the bottom layer, namely the input the feature vector. Then you'll finish the computation. We're gonna go over this in the next lecture and give a more intuitive way, like how this conducted in the vector and the matrix representation. Okay, see you on Thursday.